As you know, I am from astrophysics, which is a little bit remote from that, even though some of my research deals with how this planet came to be and how did water arrive here to Earth. And some of my colleagues also think that the ultimate solution to all the problems we have in here is to populate space. But I think it's a good idea that this center is dealing with more immediate solutions and more immediate actions that we can take. So it is my pleasure now to introduce Johan Rockström. Professor Rockström is the director of the Potsdam Institute for Climate Impact Research and a professor of Earth System Science at the University of Potsdam. Everybody in the Hebrew University should know that Potsdam, a city next to Berlin, is where the Einstein Tower is, which was built originally to verify the prediction of Einstein's general theory of relativity. Okay. Professor Rockström is an internationally recognized scientist on global sustainability issues and led the development of the Planetary Boundaries Framework for human development in the current area of rapid global change. Professor Rockström is a leading scientist on global water resources with more than 25 years experience in applied water research in tropical regions and more than 150 publications in fields ranging from applied land and water management to global sustainability. He is a member of the European Commission Expert Group Mission Board for Adaptation to Climate Changes, including societal transformations, which, as we heard in the last talk, are very much needed in here. Chair of the Earth Commission, Chief Scientist of the Conservation International, and elected member of the German Academy of Sciences, Leopoldina. Professor Rockström, please, thank you.
Thank you very much, and it's an honor to be with you, celebrating the opening of the new Center on Sustainability at Hebrew University. So let me start by joining Jeff Sachs and everyone on congratulating you at this moment. I hope you can see my slide here. What I'd like to do, sitting here actually in Karl Schwarzschild, the famous mathematician who basically was the first mathematician to solve Albert Einstein's general relativity theory equations in terms of the general relativity equations. So it is truly a science connection that we're making today. I'm not going to solve the pathway to a sustainable future. I'd like to give you an update of the scientific challenges of how humanity can navigate the Anthropocene. So, not surprisingly, I think any interdisciplinary center formation on sustainability today must have the most important scientific message to humanity over the past 3 decades as a platform, namely that we have entered a new geological epoch. We're leaving the Anthropocene, we're leaving the Holocene and we're entering the Anthropocene, anthros for us humans, that we're now the dominating force of change of planet Earth. The scale, speed, and interconnectivity exceeds even the natural variabilities and forcings from orbital forcing around the sun, volcanic eruptions, earthquakes. They're still here causing extreme events, but we're now surpassing this. We're starting to hit the ceiling of hardwired processes that regulates the state of the entire Earth system. We start feeling the impacts of this. We've caused 1.2 degrees Celsius of global warming so far. 2020 is, as you know, the warmest year on record, together with 2016. The last decade is the warmest decade on record. But not only that, we know from unequivocal science that we have crashed through the warmest mean temperature on Earth since we left the last ice age. We're truly in uncharted waters. Now the impacts are being felt. We read about it every day. We're right now experiencing the devastating heat wave in British Columbia and parts of West US, but wind back just 1 year, we had the unprecedented wildfires with devastating impacts on humans and ecosystems and wildlife in Australia. We've had now 3 consecutive extreme heat waves and freak winter conditions in Europe. We have continuous amplified human amplifications on extreme events, on floods, droughts, disease patterns around the world. So if there's a red thread in science, it is that things are changing more rapidly than we had predicted. You may have seen the WMO statement just yesterday confirming that we have another record temperature observation in Antarctica, 18.3 degrees Celsius from 6th of February 2020, which is one of the amplifying factors that both poles on planet Earth have an amplification of warming of in the order of 3 degrees Celsius already today. So if it's 1.2 average globally, we are at the Arctic and Antarctica in very different conditions already as we speak. The extreme heat wave hitting right as we speak in British Columbia, causing unprecedented impacts on humans, are difficult to explain. It's not possible to explain it only with the 1.2 degrees Celsius warming. It is not yet scientifically established what links this have with potential shifts in the jet stream and in the wave resonance created by changes in the heat gradient from a melting Arctic. But very likely there is a connectivity to the changes in the jet stream, the high atmosphere winding of air systems that controls weather systems in the northern hemisphere, and how we see increasing scientific publications showing that when the heat gradient shifts because of an Arctic melt, causing this wave resonance of a slowdown in the jet stream, locking in high-low pressure systems that have been explaining California wildfires, the extreme heat waves in Europe, very strong lock-ins of cold versus warm periods. We cannot exclude that also this occurrence that we're experiencing right now has a connection to these links. So this is also some of the lessons we're starting to learn from the global sustainability research, that we see trends of observed shifts occurring over a very long time, incrementally, changing into accelerated change, then interacting and causing feedbacks with unexpected outcomes. And that this is one of the red threads in science that is at the frontier of integrated Earth system research. We have, of course, the field research on impacts directly on life support systems on Earth. I mean, I think this is one example of how we are now able to observe from all corners of the planet, in this case, what's happening with all the glaciers. The depth of these drops are the mass loss of glaciers. We're losing mass on all glaciers on planet Earth. And as you see, there's a ground zero, again, coming out in Alaska, Greenland, the Arctic. But just look also in the third pole in the Himalayas with the geopolitical implications of losing the freshwater supply gradually in Pakistan, parts of India, parts of China and Southeast Asia. We have a handle today of the Earth system. The big question, of course, is what are the implications for human development in the future? But it's not only about climate change, as we know. It's equally important to recognize that we are in the 6th mass extinction of species, that we're undermining the biological living life support systems on Earth. 2/3 of the average size of wildlife populations have been estimated to have been lost in just one human lifetime. Basically, during the adult, I mean, I'm looking at myself here, the adults on watch on Earth today have been basically experiencing this exponential loss of biodiversity and undermining of the ecological functions and services, nature's contributions to people, but also nature's contribution to the resilience of the Earth system. IPBS, as you may know, the global scientific assessment sister of the IPCC, Intergovernmental Panel on Climate Change. This is the Intergovernmental Platform on Biodiversity and Ecosystem Services, estimated that we are on the path of extinction of one up to 1 million species of the known 8-9 million species. So this is why we can today say that we don't have one crisis in the midst of a pandemic. We have 3 crises: a climate crisis, an ecological crisis, and a health crisis. And they do interact. As you see from the right-hand graph here, you have the hockey stick of rising zoonotic virus disease outbreaks, because we know that COVID-19, just like HIV/AIDS, but also Zika, avian flu, the Nipah virus, the SARS virus, are all viruses that have spilled over from wildlife via often intermediary hosts like livestock to humans. And that this is a very rapid rise in occurrence that coincide with the Anthropocene, and that we have more and more evidence that unsustainable and risky exploitation of natural habitats with wildlife hunting, wildlife trade, interactions with livestock in an interconnected, globalized world of transport and trade is all a perfect cocktail for zoonotic viral disease outbreaks. So we should not be surprised that we, in the Anthropocene, experience pandemics. Now, therefore, we are at a new juncture. We need to think of global sustainability not anymore as an issue of reducing environmental impact, but about security, about stability, about prosperity and equity. It is no longer a question of the environment. But what I would like to do in the following is to focus on this little blue marble. We all know the famous Apollo 8 photograph from 1968. And the drama here is that from a global sustainability science perspective, we are now, for the first time, forced to address the following research question. Are we at risk of destabilizing the whole system? We've never been at that domain before. There's never been a reason or evidence that we would have to address that research question. The Earth Commission has been set up, which is the first time there's a scientific assessment body, multidisciplinary, from the earth sciences to the social sciences, exploring this question. Are we at risk of, when we now are leaving the Holocene, as shown in this visual from a paper recently published by the Earth Commission, when we cross the threshold out of the Holocene, where will we then land? We do not know that yet, because my conclusion is that we are biophysically still in an equilibrium state similar to the Holocene. The Anthropocene is so far a pressure, that humans cause the major pressure. And the big challenge for us in navigating the next decades and century is, will we roll down the slope towards an unsafe future of rising turbulence, potential crossing tipping points, and feedbacks that will undermine the ability for life support for the vast majority, particularly of the most vulnerable in the world? Or will we be able to transition towards a manageable future where we can stay in a state that can support humanity in an equitable way? So that is like the big charge. And I would argue that this is probably the biggest charge we have for humanity's future. Now, is there scientific support for this, let's say, dramatic scientific quest? I will argue, not surprisingly, that the answer is yes. One comes actually from climate modeling. This is a paper published by Matteo Willett and Andrzej Ganopolski and colleagues at the Potsdam Institute, actually, but running one of the more established EMICs, Earth System Models of Intermediate Complexity, called Climber2, a well-established model, which for the first time has been able to reproduce the journey of planet Earth during the entire Quaternary, meaning 3 million years, which is what you see on the x-axis here. So that is the so-called Pleistocene and the Holocene. Why this focus on these 3 million years? Well, of course, geology is important. We know that Earth system has been around for 4.5 billion years, but we have to recognize that it's only in the last 3 million years that we've had a planet which biologically and biophysically resembles the planet of today in terms of continental composition, chemical composition of the atmosphere, cycles of water, carbon, nutrients, and in the functioning of the biological systems. So it's only the planet of the last 3 million years that really counts as a reference point for life as we know it on Earth. On the y-axis, you have global mean temperature. The 0 point is pre-industrial temperature, meaning 14 degrees Celsius. And the green line is the simulation of a model that runs only on the physical equations as we have understood the function of the Earth system. And what's so remarkable is that when you look at this, oscillation between ice age and warm periods, how the natural forcings are pushing the planet up and down, never do we pass 2 degrees. The planet has stayed under 2 degrees Celsius during the entire Quaternary, as far as we know today. And go down to -4 to -5 degrees Celsius below the global mean temperature, the pre-industrial level, and we are in deep ice age. So the corridor of life, as I call it today, is very narrow. It is below 2 at the warmest state and -4 at the coldest state. And this is, in my mind, a very strong scientific support, of course, for the policy regime of the Paris Agreement, but also for us to avoid going through the 2 degrees Celsius planetary boundary. We are today following a pathway that takes us above 3 degrees Celsius in a blink of time, meaning in just this century. But it's even more dramatic than this, because the question is, why has the Earth system stayed within this narrow corridor? Well, it's not only because of the gentle sun or gentle volcanic eruptions or gentle earthquakes. Oh no, it's also because of the resilience of the Earth system. And we have some proof of that from contemporary observations. One of them is from the famous Global Carbon Project, with the iconic work that comes out every year mapping the carbon cycle in the Earth system. You've probably seen these graphs. The x-axis is time since the Industrial Revolution, 1850 until today. On the y-axis is emission of carbon dioxide in billion tons of carbon per year. Above the zero line, you see the classic hockey stick of fossil fuel burning in gray and land use change in orange. So we're up at 9 gigatons of carbon burned and chopped down forest each year, which is roughly the 40 gigatons of carbon dioxide per year. Is it this that has caused 1.2 degrees Celsius warming so far? Well, we know that is not the case, because in dark green, we have this remarkable uptake of carbon dioxide in the ocean, and in the light green, we have this remarkable uptake on land natural ecosystems. So it's only the blue wedge here that has caused the warming so far. And if you look at this graph, you see immediately, the more we stress this system, the more the Earth system applies its biogeochemical resilience to buffer and remain in the interglacial Holocene equilibrium state. And this is proof that a healthy planet tries to apply its biogeochemical processes to remain in its attractor, in its stable state. The drama is that we're seeing more and more scientific papers like this showing how big biomes on Earth, big so-called tipping elements being the large biophysical systems on Earth that contribute to regulate the state of the planet, are starting to show signs of instability. You may have seen just a few weeks back a seminal paper showing that over the last 10 years, the Brazilian part of the Amazon rainforest has shifted from carbon sink to carbon source, a very dramatic development indeed. So we are starting to see cracks in the ability of the Earth system to hold the planet in a Holocene attractor at a state where the planet is under tremendous pressure in the Anthropocene. Is this something we have to be really concerned about? Well, I would argue very strongly, yes. Why? Well, it's because when you take the details of the state of the planet at even higher resolution, we come to the last 12,000 years. You're probably well familiar with this final part of the ice core evidence coming both from the Arctic and Antarctica. Again, on the y-axis is middle global mean temperature, 20,000 years on the x-axis. We leave the last ice age, 70-meter lower sea level, -4 degrees Celsius takes us to that low point. We leave the last ice age and we enter this extraordinarily stable Holocene phase, what I call today even the Garden of Eden of humanity's civilizational journey on Earth. And you see the spike at the end when we start burning fossil fuels and how we are leaving the Holocene very rapidly. The Holocene is a ±1 degree Celsius state of the Earth system. It's even more narrow than the entire Quaternary corridor of life. You may ask yourself, is this really reliable data? Well, I can assure you, this is a paper from Darrell Kaufman et al. taking all the data we have on mean temperatures, observations during the Holocene, just to confirm with you that the Holocene is a plus minus 1 degree Celsius interglacial state of the Earth system. And it's particularly the second half of the Holocene that is important, the so-called Megalayan phase, because that is when sea levels on Earth also, after a delay factor, stabilize to almost perfect harmonious conditions. And we know what happened. We have quite a lot of data on how the Neolithic Revolution, once we enter the Holocene, we go from being hunters and gatherers, a few million people, we domesticate animals and plants. We start in your part of the world, in the Middle East, in the Levant, with wheat and barley, but almost simultaneously across all continents in the world, we domesticate animals and plants, and off we go in the civilizational journey that takes us to the modern world of today. So the conclusion scientifically, but also ethically, is very simple but highly dramatic, that the Holocene is the only state of the planet we know for certain can support the modern world as we know it. We've been living outside of the Holocene for certain, but we cannot give any evidence of the possibility of supporting in an ethically responsible way a world of 7.7, soon to be 10 billion people. So that's the reference point. And oh my God, we're now on the way away from the Holocene. The drama is even more, higher than that, as we know, because it's not only that the Anthropocene is a pressure point on the planet, we also have the science on tipping points. That not only do we have more knowledge of the Earth system as a self-regulating, biogeophysical, complex, self-adaptive system, we also have a better understanding that the tipping elements that regulates the state of the planet have multiple stable states separated by thresholds. The first time these tipping elements were mapped was in 2008 by Tim Lenton et al. With colleagues here at the Potsdam Institute. 10 years later, we did the update. This was published just before the pandemic as well, and it gave us quite a stark realization of the challenge we're facing. And even in our mapping, I must admit that this was quite a surprise to us. We know of 15 big climate regulating tipping elements in the Earth system. 9 of them, shown here, are in our conclusion showing signs of moving towards potential thresholds, meaning that they're showing signs of instability. And that in itself is incredibly worrying. But even more worrying are the arrows here, that we have more and more scientific evidence of interconnections between the tipping elements, that there is a kind of a cascading relationship between them. And just to give you one example of something that I've been having as a red thread here, what's happening in the Arctic and Antarctica. So the Arctic summer ice and Greenland is melting very fast, releasing cold, fresh water into the North Atlantic, contributing to slow down the AMOC, the Atlantic overturning of heat in the ocean, which in turn is impacting on the monsoon system over South America, which can explain the higher frequency of droughts and forest fires, releasing even more greenhouse gases from the Amazon, which is destabilizing. But it also holds warm surface water in the Southern Ocean, which can explain the accelerated melting of the Thwaites Glacier and other West Antarctic ice shelves, accelerating sea level rise. So you see there's a connectivity here between the two ground zeros, the Arctic and Antarctica, across different tipping elements that are connected. And the evidence behind this, as you may know, is increasingly published in the literature. Here you have the Lettre-Cesar et al. Paper on the slowdown of the AMOC, a 15% slowdown observed so far. We have more and more scientific papers coming out on tipping point risks in the Amazon, with Tom Lovejoy and Carlos Nobres leading top global environmental change scientists in Brazil, saying that if we cut down more than 20 to 25% of the rainforest area, combined with the global warming we're seeing so far, we can be at a tipping point and irreversibly shifting the rainforest toward a savanna state. We are today at 17%, so uncomfortably close in my mind. So it's not surprising that when combining all this evidence on the Anthropocene, that the Holocene is the Garden of Eden, our reference point, the human dependency of the Holocene, and that tipping points are real, that we tried to advance as one gap filler in global sustainability, the planetary boundary framework, trying to define what are the systems and processes in the biophysical function of the Earth system that regulates the state of the planet. And if we want to stay in a Holocene state, what are the quantitative scientific targets for a safe operating space shown in green, recognizing uncertainty yellow, and quantifying a guide for humanity's ability to navigate the Anthropocene. And 4 of the 9 boundaries are today, the latest assessment in 2015. We're now working on the 3rd update on the planetary boundary science, showing that we are in a risk zone. And we see more and more signs verifying this. Like, for example, the bleaching of coral reef systems, like, for example, the risky trajectories we're seeing on permafrost thawing in Siberia and across the Arctic. As I mentioned earlier, the published papers on the irreversible melting of some of the glaciers in West Antarctica, that this may have a hysteresis impact, that we may push West Antarctic ice shelves across irreversible melting at a very low temperature, but it's very difficult to freeze them back because a much lower temperature will be required for any reversed process. And you may have seen recently the conclusion by a group of scientists from AVI University in Bremen that very likely we are already on an unstoppable journey on losing Arctic summer ice, which is a drama in so many ways. I mean, both human and ecological, but also in terms of losing one of the albedo cooling components of the Earth system and the impacts it may have on the jet stream. So I think we have a lot of evidence today that there's a new type of global sustainability required in the Anthropocene, which is to combine Earth system stability with human prosperity and equity. Can this have very important impacts? Well, Jeff Sachs already pointed at some of this. Let me just heighten the scientific evidence of this even further. We have more and more science showing that just the heat waves we're seeing today can lead to higher degree of intolerable temperatures, mortality at roughly 30 degrees Celsius as a kind of a threshold point between manageable and unmanageable temperatures. A few months back, there was from the Exeter University in the UK, a study showing the risks we're facing with regards to human health combined with heat waves caused by climate change. This is a classic colored map on the vulnerability of economies. So the dark red are the most vulnerable, fragile economies. The blue-green are the OECD regions, basically, the more wealthy economies in the world. The black spaces here, the dots you have in the Sahara Desert, are the regions that today have a global mean temperature exceeding 29 degrees. So we have very limited geographical area and 100 to 150 million people living in these extremely hot regions. The hashed zones is the estimated area under more than 29 degrees Celsius of average annual temperature if we continue business as usual up until 2070. So just in 50 years' time, we would have Brazil, West Africa, Middle East, Horn of Africa, India, and Southeast Asia under intolerable heat conditions right through the year. This is 3.5 billion people. And of course, it's the most vulnerable that will not afford air conditioning under these extreme conditions. A recipe for instability, displacement, and potential migration away from these conditions. And we have more and more science showing that the red zones will become even deeper red, because in the upper graph here, you have one of the latest assessments on how climate impacts will reduce GDP levels in the red economies with more than 20%. So you have this very vicious cycle of heat waves, health impacts on vulnerable economies that will become even more vulnerable, a recipe for destabilization. So this is what we do not want happen. We really need to transition away from a security perspective, not only a sustainability from an environmental sustainability perspective. In a few final minutes, just to say that the journey ahead is a transformative one, as Jeff Sachs pointed out. We need to land in a net zero world economy by 2050. We need to follow what we call a carbon law, which means cutting emissions by half every decade. We're emitting roughly 40 gigatons of carbon dioxide today. If we cut that by half every decade, we have a residual difficult to abate part that we can compensate through CCS and BECCS by 2050. That will give us the ability of landing well below 2 degrees Celsius. But I want to leave with you that this will not be enough. It may actually be, a bit provocatively, the easy part of the story. Because in order to have any chance of landing within the quaternary narrow corridor of life, we need not only to follow the carbon law and have a net zero world economy shown here in gray, we also need over the next 30 years to transition the world food system from the world's single largest source of greenhouse gases, shown in the brown wedge, to become a sink of carbon by 2050. This is an agricultural revolution, which is also a prerequisite for us to be able to land within the corridor. But not only that, we also need to accept scaling of negative emission technologies, CCS and BECCS, shown here in the orange wedge. But not even that is enough. We're also basically counting in, we're already factoring in to the climate models of the IPCC an assumption that the planet remains stable, that we do not cross tipping points, that the green wedge of carbon sinks on land-based ecosystems will remain intact, that the blue wedge of the oceans will remain intact. And if all this happens, decarbonize the energy system, transform the food system, scale negative emissions, and keep the resilience in natural systems intact, we have a 66% chance of staying well below 2 and a 50% chance of reaching 1.5. So not even really good bets of success. But it's just to emphasize that it's truly, truly a global sustainability transformation that we are facing over the coming decade and decades. So we need some new thinking. And of course, I think what Partha Dasgupta presented in the economics of biodiversity is one step in the right direction of recognizing that now we need strong sustainability for economic development, meaning that we have to have an economy that internalizes all externalities, that works in line with Jeff Sachs' points about equity and ability of working in harmony with nature, but doing it within planetary boundaries. The Earth Commission has been set up to serve this, to be a scientific commission to provide quantitative, safe, and just targets for businesses, cities, and nations around the world. A kind of a new, filling a gap in the global sustainability agenda. And as you may know, this is a special year. We have the UN Food Summit, we have the Chinese Summit in Kunming on biodiversity, and we have COP26 in the UK. And we are seeing the emergence of a science-based target also for nature, the 1.5 degrees Celsius equivalent for nature, of saying enough is enough. Scientifically, we cannot no longer afford to lose intact biodiversity and ecosystems, that we need to have a net zero loss of nature and have regenerative efforts to reach a net positive point by 2030, to have a recovery by 2050. It's quite interesting to see how we are shifting towards an integration between economics, with economic incentives and policy tools, together with science-based targets for a safe operating space as a kind of a combination for sustainability. So it's illustrated here, coming actually from the policy domain. This is not a scientific graph. This is how policy itself is preparing for the dialogues in Kunming of how stopping biodiversity loss now and trying to rise up from 2030 onwards. I want to leave you with this final graph, just because I realize I've been doing just the diagnostic today, to say also that there is, of course, a tremendous momentum in the world in the right direction also. We see the three largest economies in the world, the US, the European Union, and China, standing up behind science, actually, and accepting, just as Jeff Sachs pointed out, net zero targets by 2050. The world is starting to move. And I think today it's not a question whether we will have a phase out of fossil fuels. The big question is, will we do it fast enough? And that is where the transformative science of how we need to integrate social and economics and natural sciences is so important. And I leave you with the kind of, I hope, inspiring framing that the way I define sustainable development in the Anthropocene is prosperity and equity within planetary boundaries, meaning that we have to have a full people's health, planetary health integration. The Sustainable Development Goals must be achieved within a stable and resilient Earth system. That's our charge. I think that's one element that could be interesting to collaborate with the new center at Hebrew University. And with that, thank you so much, and back to you.
Thank you very much. I would like to ask a short question. From your experience, what is the action you would recommend for our university and for this new center to take in order to most efficiently direct research to face the challenges that you mentioned in your talk?
That's a very good question. It's a big question, and I think it has many dimensions to it. I mean, to begin with, I think one should be honest and a bit humble when taking on, let's say, interdisciplinary global sustainability science today, and invest within a new center, but also at a very early stage establish strong scientific links with other centers of excellence in the world, and see this as a, let's say, as a collective charge, as a kind of a community effort. So that would be one. Secondly, my advice would be, I think a center like yours could also try to identify a kind of a flagship initiative of where would you want to really contribute to fill a gap in the evidence we need for a transition towards a sustainable future. And then third, I think it's also a question of truly, I mean, if you want to really make a fast contribution, I think one of the critical issues is how to connect different cultures. I mean, the whole social science dimension with the physics and the economics. I mean, that kind of true, to dare to do a true integration. And I think you're sitting in a very good position for that, because you have, let's say, the wings of history right next to you. And I think kind of getting that human dimension at the center of the sustainability science, I think, is one of the biggest challenges, but also one of the most rapid ways forward.
Thank you very much.